Wait, so you're telling me we are burning thousands of GPU hours, like literally melting silicon inside these multi-million-dollar data centers, just waiting for an AI to finish writing a single line of Python?
Yeah.
And while that's happening, the rest of the cluster is just sitting completely idle.
That is the exact mathematical reality of most reinforcement learning pipelines today.
Wow.
You have these massive compute clusters effectively acting like a dial-up modem, because of how the underlying optimization algorithms are structured.
From an engineering perspective, that is just a complete nightmare. I mean, picture a convoy of sports cars on a highway.
Okay, I'm picturing it.
You've got these incredible machines, right, engineered from the ground up to go 200 miles an hour. But for some reason, they're forced to travel behind a golf cart.
Oh, wow. Yeah.
And because the rules of the highway dictate that they absolutely have to stay in tight formation, the entire convoy, all that raw horsepower, is doing like 10 miles an hour.
Here's the thing, though. The second you try to let those sports cars break formation and speed ahead,
to fix the traffic jam.
Right, exactly. The second you switch to asynchronous training to fix that jam, you completely break the underlying math of the reinforcement learning system.
Wait, really? Break it how?
Well, you solve the efficiency problem, but you destroy the AI's ability to actually learn anything stable. It just crashes into the guardrails.
Okay, let's unpack this, because we are looking at a paper today that claims to have solved exactly this computational traffic jam without, crashing the cars.
Yeah, it's huge.
It's a fascinating piece of research from Tsinghua University titled Single-rollout Asynchronous Optimization for Agentic Reinforcement Learning, or SAO.
Right, SAO. And for anyone who has been tracking the absolute arms race in post-training for large language models, this feels like a massive puzzle piece falling into place.
It's a critical piece of the puzzle, especially right now in 2026.
Yeah.
I mean, the shift from standard chat models to fully autonomous reasoning agents has exposed massive flaws in how we do reinforcement learning. Right. And in this deep dive, we're going to tear down how they engineered this exact solution.
It gets pretty wild.
It really does. We'll look at why the current reigning champion of post-training, which is GRPO, is fundamentally flawed for complex agentic tasks, and how the researchers use some incredibly aggressive mathematical clipping to fix the chaos of asynchronous learning. But before we get to the heavy math, I want to ground this in the physical reality of the hardware.
Okay, let's do it.
Let's go back to that traffic jam. I want you, the listener, to picture something we have all lived through. The dreaded school group project.
Oh, the absolute worst.
You know exactly the dynamic I'm talking about. You have a group of 4, the assignment is given out, and 3 of the group members are highly motivated.
Right, for achievers, right.
They finish their sections of the report on Monday. They are done. Their parts are ready to submit. But the inflexible rule of the group project is you cannot hand it in until the whole document is stitched together.
And there's always that one person.
The straggler.
Always a straggler.
They take 5 days to write their single paragraph. So for Tuesday, Wednesday, Thursday, and Friday, the rest of the group is just sitting there, paralyzed.
Just waiting.
Exactly.
Yeah.
They can't start the next assignment. They can't submit this one. They're just burning time waiting. That trauma, that very specific structural inefficiency, is exactly how standard reinforcement learning algorithms operate right now.
It's the perfect analogy for synchronous group-wise sampling. To connect that to the actual technology, we need to look at algorithms like proximal policy optimization, PPO, and especially the recent industry darling, group relative policy optimization.
GRPO.
Right, GRPO. When we train these models to align with human preferences or solve math problems, we ask them to generate a bunch of possible responses to a single prompt.
And these attempts are called rollouts, right?
Exactly, rollouts. Now, in the old days, when we were just training models to write a polite email or summarize a short news article, all the rollouts took roughly the same amount of time.
Like 10 tokens here, maybe 50 tokens there.
Yeah, exactly. The group project members all finished their work on Monday.
Right, but the landscape of what we demand from these models has shifted entirely. I mean, we aren't just asking for polite emails anymore.
No, not at all.
We are asking for autonomous agents. We are asking for coding workloads that require deep search, complex mathematical reasoning that requires chain of thought.
And in those agentic workloads, the rollout lengths vary wildly. The variance is just staggering.
Give me an example of that variance.
Okay, so you might give the model a complex reasoning prompt, And one of the rollouts it attempts is a very quick hallucination. It just says, yes, the answer is 4.
Dumb.
Right, that's 10 tokens. It finishes in a fraction of a second. But another rollout for that exact same prompt might involve the model writing a Python script, executing it in a sandbox, realizing there's a logic bug.
Oh man, reading the compiler error.
Yeah, rewriting a massive nested loop and simulating it all over again. That single rollout could easily balloon to 100,000 tokens long.
So you literally have the kid who finishes the paragraph on Monday and the kid who takes 5 days.
Yep.
But because current popular methods like GRPO use what is called group-wise sampling, the underlying system architecture absolutely has to wait.
Yes. GRPO calculates how good a specific rollout is, its advantage, by comparing it to the average performance of the entire group.
Right. So you generate, let's say, 8 parallel rollouts for a prompt.
And you physically cannot know the average score of those 8 attempts until all 8 are completely finished and evaluated.
Wow.
So the entire multi-million-dollar GPU cluster, which is capable of processing trillions of floating point operations per second, is forced to act like that frustrated group project team.
It sits paralyzed, memory locked up.
Just waiting for the slowest 100,000 token trajectory to finally terminate.
Which brings us to the obvious first principles engineering fix. If waiting for the group is the fundamental bottleneck, just kill the group constraint.
Just get rid of it.
Yeah, restructure the pipeline. Process the rollouts continuously as they arrive. If a short 10-token rollout finishes, don't wait for the 100,000 token monster to wrap up.
Right, just process it.
Just take that short rollout, calculate the reward, calculate the gradient, and update the model weights immediately. Keep the GPUs fed with constant matrix multiplications.
Keep the sports cars moving.
Exactly. Keep the sports cars moving at 200 miles an hour. That's asynchronous reinforcement learning. Efficiency problem solved, right? We can all go home.
Well, here's the thing, though. While you solved the hardware utilization problem beautifully, you just introduced a mathematical nightmare.
Oh, no.
Yeah, it's known in the literature as policy lag, or off-policy drift.
Okay, what exactly is policy lag? Explain the mechanics of it to me. What is happening under the hood when we decouple these updates?
Imagine the distributed architecture, okay?
That.
You have the main model, the one you are actually updating and training, the actor whose weights are actively changing.
Okay, the training model.
Right. We'll call it the training model. It sends a copy of its current neural weights to the generation servers across the network to start creating those rollouts.
Got it.
Now, let's say it starts generating that massive 100,000 token coding rollout. That's going to take a long time to compute, even on like H100s.
Sure.
Meanwhile, the generation servers are also churning out short rollouts, which finish instantly. Because we are asynchronous now, the training model takes those short rollouts, calculates the loss, and immediately updates its own internal weights.
So it learns from them. It changes.
Yes.
Yeah.
The model evolves. Its internal state is fundamentally different than it was a few seconds ago.
But wait, the generation server is still churning away on that massive coding rollout.
Exactly, using the frozen copy of the older version of the model. By the time that huge rollout finally finishes, gets its reward from the environment, and comes back across the network to the training model has already updated itself dozens, maybe hundreds of times based on other asynchronous data.
Oh, wait, so you're telling me the massive rollout that just arrived at the training server was generated by a ghost?
Yes, a ghost.
It was created by an older, completely different version of the model that technically doesn't even exist anymore.
Precisely. And in reinforcement learning, the core mathematics, the policy gradient theorem, relies entirely on estimating the advantage of an action based on the current policy.
Right. You were trying to figure out, if I take this action right now, is it better than my current average expectation?
Exactly. So if the rollout came from a vastly different, older policy, the math just breaks down.
The training model looks at it and goes, who did this?
Pretty much. It looks at the trajectory and the log probabilities and says, wait, my current weights would never generate these tokens with these specific probabilities. This data is alien to me.
Wow.
The gradient updates become chaotic, the vector directions swing wildly, and the training completely destabilizes. You melt the silicon efficiently, but you get mathematical garbage out.
That is fascinating. You can't penalize or reward a model for something a ghost did 3 evolutionary stages ago because the gradient you calculate won't map to the current neural pathways.
Nope, it just scrambles everything.
So how did the industry handle this off-policy drift before this Singhua paper? Because I mean, asynchrony isn't a brand new concept in computer science.
It's not, and the traditional mathematical fix is called importance sampling.
Hmm.
Basically, to correct the off-policy drift, the system has to figure out exactly how much the model has drifted.
Okay, how do you do that?
For every single token, you have to calculate the probability of the old ghost model generating that action and divide it by the probability of the current model generating that exact same action.
Ah, so that creates a ratio.
Right. If the ratio is close to 1, the models agree. If it's far from 1, you scale the gradient update down to penalize the drift.
Okay, so logically, to do that division, you just have to keep the old model around to ask it for its probabilities.
But here is the massive infrastructure problem with that. Which old model?
Oh, right, because it's asynchronous.
In a highly asynchronous distributed system, the generation engine might have gone through multiple different weight updates while generating a single long trajectory.
Oh, man. So the beginning of a 100,000 token trajectory might have been generated by version 1.
The middle by version 5, and the
Yeah.
end by version 12.
That's a mess.
To do exact importance sampling, you would have to maintain a massive historical archive of old model checkpoints in VRAM.
Let me just do the math on that. These are huge models. We're talking 30 billion, maybe 750 billion parameters.
Huge.
A 750 billion parameter model at 16-bit precision takes over a terabyte of VRAM just to store the weights. You can't just keep an archive of a dozen of them sitting in memory.
Exactly. You would need dedicated server pods just to store the ghosts.
The memory footprint would be economically catastrophic. It completely defeats the whole purpose of being hardware efficient in the first place.
Right. It's computationally prohibitive at modern LLM scales. Which brings us to the first major conceptual innovation in the SAO paper.
All right, lay it on me.
They introduce a mechanism called direct double-sided importance sampling, or DIS. And it is beautifully brutal in its simplicity.
Let's break down the direct part first. How exactly do they avoid keeping that massive terabyte-heavy archive of ghosts?
They drop the old policy tracking entirely. They literally just throw the ghosts away.
Just delete them?
Just delete them. Instead of trying to maintain a history of model checkpoints in VRAM to calculate the exact old probabilities, they just look at the network logs.
Okay, how does that work?
When the rollout engine generates a token, it inherently calculates a log probability for that token. That's how the next token prediction works.
Right.
SAO simply mandates that the generation server saves that specific log probability right then and there, bundling it with the token. It uses the rollout policy itself as the behavior proxy.
So it's essentially saying, I don't care what version of the model you were when you generated this token, just stamp your exact confidence score on the token before you hand it back over the network. And then the training model just compares its current confidence against that stamped score.
Exactly. That stamped score serves as the denominator in the importance sampling ratio.
That is incredibly pragmatic. Wait, let me push back on this.
Go for it.
If you are dropping the exact tracking and just trusting whatever stamped log probability comes back, aren't you accepting a massive amount of inaccuracy? Especially if the environment is shifting. You are trading mathematical purity for computational feasibility.
You absolutely are. You are explicitly accepting a controlled degree of off-policy bias. But to prevent that bias from blowing up the gradient calculations, SAO introduces the double-sided part of DIS.
Okay.
And this is where the paper gets highly aggressive with its clipping strategy.
Let me try to visualize this math. I want you to picture a highly strict bouncer at a very exclusive nightclub.
Oh, I like this. Walk us through it.
The bouncer has a clipboard. This clipboard represents the trust region. In the paper, they define this region as a strict mathematical interval, right? 1 minus epsilon low to 1 plus epsilon high.
Right, the VIP list.
Yeah, exactly. When a token tries to enter the club, meaning when it tries to be used to calculate a gradient update for the neural network, the bouncer checks the probability ratio between the current policy and the stamped rollout policy.
Yep.
If that ratio is too high, meaning the current model thinks this token is way more likely than the ghost model did, or if it's too low, meaning they vehemently disagree.
The bouncer doesn't just ask them to step aside or scale down their influence. The bouncer completely masks them out.
Exactly. You are denied entry. The gradient goes to absolute zero.
Zero. Just totally ignored.
The token is completely ignored by the backpropagation pass. Standard PPO clipping, which most of the industry uses, usually just caps the value.
Right, it just limits the extreme ends.
It clips the extreme end so the update isn't too large,
Yeah.
but it still lets some signal through to pull the weights. But SAO is ruthless. If the divergence falls outside the VIP list on that clipboard, the token is dead to the system.
It's an incredibly aggressive way to stabilize mathematical chaos.
Yeah. If the current model and the ghost model disagree too much, we just pretend the token never existed.
And that ruthlessness is exactly why it mathematically works.
Yeah.
By utilizing the rollout log probabilities directly from the generation phase, they completely eliminate the computational overhead of separate old policy inference.
Saving terabytes of VRAM.
You save terabytes of VRAM, and by using that strict bouncer, that double-sided masking, they strictly bound the variance that arises from extreme policy divergence.
So it's safe.
Very safe. The empirical results in the paper prove that this simplified, aggressive mechanism effectively regularizes the updates. It keeps the gradient norms from exploding, yielding superior stability in these asynchronous settings.
Okay, so we've fixed the off-policy drift. The bouncer's keeping the club safe. The gradients aren't exploding. The sports cars are speeding along asynchronously.
Everything is moving fast.
So why can't we just take GRPO, the current king of the hill for reasoning models, slap this diz bouncer on it, and run it asynchronously? Why do we need the rest of this paper?
Because GRPO has a foundational structural mismatch with complex agentic environments. It's right there in the acronym. Group Relative Policy Optimization.
The group part.
GRPO inherently mathematically requires a group to function.
Right. Because to calculate the advantage, to know if a specific rollout was actually good or bad, GRPO looks at all the rollouts for a single prompt, averages their rewards to create a baseline, and says, okay, rollout number 3 was better than the average, so we increase its probability.
And rollout number 5 was worse than the average, so we decrease its probability. It absolutely needs siblings to compare against.
But think about an online dynamic agentic setting. Picture a real-world deployment where an agent is interacting with a user in a terminal, or navigating a live web browser to book a flight.
Right. Totally different.
The environment doesn't give you 8 parallel universes to try different browsing paths and see which one is best. The environment gives you exactly one trajectory per prompt.
A user asks a question, the model issues a command, the environment responds. That's it. One sample.
You physically cannot calculate a group average of 1.
Exactly. Group-wise sampling is fundamentally incompatible with online learning or environments where feedback is interleaved, singular, and state-dependent.
So what's their solution?
SAO proposes killing the group entirely. They introduce single rollout sampling. One prompt, one rollout, immediate update.
Wait, that broke my brain. If you only have one rollout, what are you comparing it to?
That is the million-dollar question.
How do you calculate the baseline? If I run a race by myself and finish in 10 minutes, is that a good time? I have no idea. There's no group average to compare it to. How does the mathematical formula calculate relative advantage without a group baseline?
It reintroduces a critic, or more formally, a value model.
We are bringing back the classic actor-critic architecture from the early days of deep reinforcement learning.
We have to. If you don't have a group of peers to compare yourself against, you need an expert judge sitting on the sidelines.
Okay, I like that. The judge.
The judge's job is to look at the track conditions and tell you what a good time for that race should have been. The value model looks at the current state, looks at the prompt, and predicts what the expected total reward should be from that exact point forward.
Okay, so it predicts the score.
Then, when the rollout actually finishes and gets a real reward from the environment, you compare the real reward to the value model's prediction. That difference, the temporal difference error, becomes your advantage.
Okay, I follow the theory. But wait, I have to push back here.
Go ahead.
Isn't there a very specific reason the industry moved away from value models and towards things like GRPO? I remember reading that training a separate value model for these massive 70 billion or 750 billion parameter LLMs was just a total nightmare.
Oh, it's brutal.
It literally doubles the memory footprint because you need a second massive neural network, and critics are notoriously unstable during training.
You are 100% correct, and the authors of the SAO paper are highly aware of this. Single-rollout RL has terrifyingly high variance.
Yeah, I'd imagine.
If your judge, your value model, is bad at predicting the expected score, it creates noisy garbage advantages. And if you feed noisy advantages into your policy model's gradient updates, you destroy the policy.
The judge essentially gives the runner wildly inaccurate feedback, and the runner starts tripping over their own feet trying to adjust.
Exactly.
So how do they rescue the value model? Because if this whole single rollout asynchronous dream relies on a stable judge, and judges are inherently unstable at this scale, the whole house of cards falls down.
The paper dedicates a massive portion of its focus to exactly this, Practical, heavy-duty value model engineering.
Okay.
They essentially had to figure out how to stabilize a massively parameterized critic. They introduced 3 specific architectural and training fixes.
And these are the kind of pragmatic, in-the-weeds engineering tricks that make a paper actually deployable in a real data center.
Exactly.
Let's walk through the causality of this. What's the first thing they tried?
The primary source of instability is the interdependence between the actor and the critic. The policy model is changing rapidly because it's updating asynchronously, right?
Right.
If the critic doesn't adapt fast enough to the new policy's behavior, its predictions become outdated. It's judging a runner who has already changed their stride.
So what's the fix?
Faster value update. They decouple the optimization frequencies of the policy and the value model.
What does that mean numerically?
Normally, in standard PPO, when you update the actor, the policy model that generates text, you also do one gradient update to the critic, the value model, 1 for 1.
Got it.
But SAO sets a hyperparameter, k, to equal 2.
Meaning for every one time they update the policy model's weights, they force the value model to run 2 optimization steps.
Exactly. The judge goes to training camp twice as often as the runner.
That's a great way to put it.
By enforcing 2 updates to the value network for every single gradient update applied to the policy, they force the value estimates to track the shifting policy much more tightly. It reduces the variance of the advantage estimation significantly.
That makes logical sense. You want the teacher to be mastering the curriculum faster than the student is progressing. But I'm guessing updating the judge twice as fast introduced its own problems.
Oh, it definitely did. During their pilot experiments, they noticed something mathematically alarming. The value model was still wildly unstable, but the instability wasn't uniform across the network.
What do you mean?
When they analyzed the gradient norms, basically tracking how violently the mathematical vectors were swinging during backpropagation, the gradients for the value model were massive compared to the policy model.
Yikes.
But when they decomposed those gradients layer by layer, they found the explosions were happening almost entirely in the full attention layers.
Huh.
The mixture of experts layers, the MOE projections, were actually relatively stable.
Okay, wait, let's break that down for a second. In MOE layer, a mixture of experts layer is essentially a routing mechanism. It sends a token to specific specialized feed-forward networks based on what the token is.
Right.
But the attention layer is what figures out the context. It's the part that looks at the whole sequence and says, this pronoun refers to that noun. And you're saying the contextual part was the part having the mathematical panic attack.
Precisely. The attention matrices were over-updating and shattering the model's stability.
So what's the pragmatic engineering fix?
Well, what would you do?
The brute force answer is you freeze the attention layers. You just turn off their ability to learn. You set requires regrad a grad, false on all the attention blocks, lock those weights in place during reinforcement learning, and you only allow the MOE layers to update.
That's exactly what SAO does. It's called frozen attention training.
But wait, if you freeze the attention layers, aren't you severely capping the model's ability to learn new contextual relationships during the reinforcement learning phase? You're basically blinding the model from learning how to read better.
You would be if you were training from scratch. But the hypothesis behind why this works here is brilliant.
Okay.
These models have already been through massive pre-training on trillions of tokens and extensive supervised fine-tuning. The pre-trained attention weights already know how to read perfectly.
Oh, of course.
They already possess the semantic capability to attend to relevant tokens across a massive context window. They understand complex grammar. They understand Python syntax. You don't need to reteach them how to read during the RL phase.
Oh, I see. The RL phase isn't about teaching the model how to understand text. It's just about teaching it which text leads to high rewards.
Exactly. By restricting optimization to just the MOE layers, you allow the model to learn the specific value function, which experts to route to for high rewards, but you effectively regularize the entire architecture.
Smart.
You stop the attention gradients from exploding without losing the expressive power needed to learn the value function.
I have to admit, that is an incredibly elegant, get-it-done solution. The attention mechanism is hyperventilating. Just unplug it.
Yeah.
It already knows its job anyway.
Yeah.
Okay, so we're updating the judge twice as fast, and we've put blinders on its tension layer so it stops exploding. Is that enough to stabilize it?
Almost. There is one final piece: scaling value pre-training. This addresses the infamous cold start problem.
Right. If you start the asynchronous reinforcement learning process, and the critic has never actually evaluated a single race before, its very first predictions are going to be random noise.
Right. And in a single rollout asynchronous environment, if the first few advantage calculations are random noise, the policy model will immediately update its weights based on that garbage, pushing itself into a destructive state before the critic ever has a chance to learn what a good score actually is.
So you can't start them simultaneously from scratch. You have to give the value model a massive pre-training corpus before the asynchronous RL pipeline even spins up. You have to show the judge millions of historical tapes of previous rollouts and their actual scores, so it has a robust, highly accurate initialization point.
Without that massive pre-training, the early stages of single rollout updates are mathematically unrecoverable.
Okay, so let's summarize the architecture before we look at the actual scoreboard. We have a fully asynchronous distributed setup. The cluster is churning out rollouts nonstop. No waiting for the group project straggler.
Continuous generation.
As soon as a rollout finishes, it's sent back to the training model. The training model looks at the rollout's internally stamped log probabilities. The strict balancer, the double-sided importance sampling clipping, mathematically checks if the divergence is within the VIP trust region.
The bouncer does its job.
Right. If it's too far off, the token is masked out and its gradient goes to 0. If it's good, we proceed. But since we don't have a group average to compare against, we ask our highly engineered value model critic for a baseline expectation.
And that critic is ready.
The critic is stable because it's massively pre-trained, it's getting its weights updated twice as fast as the main model, and its attention layers are completely frozen to prevent gradient explosions. That is a deeply engineered, highly defensive software system.
It is deeply defensive, but the offensive capability it produces is staggering. Which brings us to the hot takes section.
Let's do it.
Let's look at the benchmarks. Let's evaluate if the hype around this paper holds up as of July 2026.
I have the data right here. And honestly, looking at these numbers, the hype is entirely justified. Let's start with SWE-Bench Verified.
For context, this is a brutal multi-step coding benchmark.
It really is. No. You don't just ask the agent to write a function. You give the agent a real-world open-source GitHub repository issue, a massive legacy code base, and it has to autonomously navigate the repo, use grep to find the bug, write the patch, and verify it.
So hard.
The baseline model they use, Qwen330B, which is a 30 billion parameter model, gets 23.0% on this.
Which is already a very respectable baseline for a model of that size.
It is. Now, you apply standard synchronous GRPO, the current industry favorite. It bumps that score up to 27.0%, a solid 4-point gain.
Pretty good.
But when you apply the full SAO pipeline, it pushes it to 29.8%. That is a massive jump on a benchmark as rigorous as SWE-Bench.
And if you think that's impressive, look at the math reasoning capabilities. AIME2025.
Oh man, the math benchmarks.
This is elite-level, highly abstract high school math Olympiad problems. The baseline Qwen3 model sits at 80.4%. Standard GRPO gets it to 84.2%.
And SAO hits an astonishing 97.3% accuracy. Let me repeat that. 97.3%. It absolutely crushes GRPO.
It really does.
A 13-point gap on AIME is not an incremental engineering tweak. That is a paradigm shift in how effectively the model is exploring the solution space.
It is a massive leap, but plot twist.
Oh, here we go.
I want to draw your attention to a very specific detail in the paper, because those impressive GRPO numbers, the 84.2%, they are hiding a very dark secret about the stability of current methods. Look at figure 3 in the source text.
Let me pull that up. Whoa, that is an ugly chart.
Exactly. Figure 3 plots the performance of these models across the actual training steps over time. The scores reported for vanilla GRPO in the benchmark tables. Those are just its peak valid performance before it completely faceplants.
Well, I'm looking at the trajectory for AIME2025 right now. The blue line, SAO, starts around 80%, and it just climbs steadily, beautifully, all the way up past 95% over 1,000 training steps. It looks exactly like a healthy learning curve should look.
Just nice and smooth.
But the red line for vanilla GRPO, it climbs a little bit, hits about 85% at step 160, and then it literally plummets straight down off the graph. It collapses back to 0.
Complete mathematical training collapse. The variance and the off-policy drift in the asynchronous environment literally destroys the model's neural pathways.
That's insane.
The weights either explode to infinity or collapse to 0. What you are seeing on that chart is the mathematical manifestation of trying to update a complex system based on the actions of a ghost, without strict safeguards. The variance tears the model apart from the inside out.
That is easily the most damning chart in the entire paper. It proves empirically that you simply cannot run GRPO asynchronously at scale. It is fundamentally unsafe. Meanwhile, SAO trains stably for over 1,000 steps.
That double-sided clipping bouncer is doing incredible work keeping the gradients in check.
It really is.
But while we're analyzing the data, I want to challenge one of your core engineering intuitions, because there is a very deep, very interesting disagreement buried in the appendix of this paper regarding exactly how we should calculate value in these systems.
Okay, bring it on. Where am I wrong?
Let's set the scenario. When an agent is navigating a complex environment, let's say it's using a web browser tool. The model thinks for a bit. It issues a JSON command to click a button. The browser loads a new page. The agent reads the HTML of the new page, and it thinks again.
The multi-turn trajectory.
Right. Now, SAO calculates the value and the advantage at the absolute micro level, the token level.
Right.
Every single word, every single comma, every single bracket the model generates gets its own individual reward expectation from the critic.
Right, and from an engineering perspective, that feels inherently wrong to me.
Tell me why.
Why are we calculating value at the token level for multi-turn reasoning agents? If an agent takes a whole step, meaning it writes a full paragraph of internal monologue and then executes a specific Python command, that whole sequence is one logical action. It's a full conversation turn.
Logically.
We should just calculate a single aggregated advantage for that entire step and apply that same scalar advantage to every token inside the step.
Walk me through the computational logic of why you think that's better.
Because it smooths out the variance in the noise. If I type print hello world, the specific intrinsic value of the left parenthesis token isn't what matters. The value is in the complete functional command executing.
I see your point.
If you try to force the value model to predict the value of every single microtoken, your critic is going to be vibrating with noise. It's going to be guessing wildly. A step-level advantage is cleaner. It's computationally cheaper because you aren't running as many calculations, and logically, it makes more sense for macroscopic reasoning.
I disagree completely. And more importantly, the empirical data disagrees with you.
I am allergic to hype, but I trust data. Hit me with the numbers.
Pull out Appendix A.1 of the source text. The researchers actually had the exact same intuition you did.
Oh, really?
Yeah. They hypothesized that token-level prediction might be too noisy for complex reasoning, so they explicitly built and tested step-level variance. They tested two specific alternatives. Step-level average, where the value assigned is the mathematical average of all tokens in the step, and step-level last token, where the value of the entire step is just the prediction logged on the final token before the environment responds.
And what were the results on the reasoning benchmarks?
On the AA2025 dataset, the token-level model, the one evaluating every single comma and bracket, achieved 89.8% accuracy.
Okay, and the step-level ones?
The step-level models, they completely plateaued. The best one, the last token variant, got stuck at 87.3%, and the average variant was crippled at 85.8%.
Wow. Okay, I stand corrected. The data objectively proves my intuition wrong. But why?
Yeah.
Mechanically, why does the noisy, vibrating, micro-level token advantage outperform the mathematically smoothed-out step-level advantage? What is happening in the gradient?
It comes down to the core issue of reinforcement learning, the credit assignment problem. Token-level calculation provides fine-grained supervision.
Fine-grained, right.
In complex logical reasoning, the difference between a brilliant deduction and a catastrophic hallucination might literally be a single word. It might be a single operator change from a plus sign to a minus sign in a massive equation.
Right.
If you smear the reward across the entire paragraph by averaging it, the model doesn't know which specific part of its logic was the brilliant move and which part was just grammatical filler.
Oh, I see.
It needs to know exactly which token shifted the probability trajectory towards success. By smoothing out the noise, you are also fundamentally smoothing out the critical signal.
That actually makes profound sense. It goes back to the group project. If you grade the whole group project with one single averaged grade, the slacker who wrote one sentence thinks he did a great job, and the genius who wrote the rest feels undervalued and learns nothing.
Exactly. You have to grade every individual contribution. Token-level grading.
Okay, I can see the point. The math supports token-level fine-grained supervision.
Speaking of token-level calculations, this brings us perfectly to the demo section of our deep dive. We want to break down the exact configurations and novel mechanics of this paper as if we were walking you, the listener, through the actual Python codebase.
And there's one specific mathematical trick in this paper that addresses exactly this multi-turn agent problem.
Let's get into it. Demo 1. The skip observation, GAE.
And let me set this up by saying, here is where most engineers get it entirely wrong when building agentic RL pipelines.
Set the scene for us. What does the trajectory look like?
Picture a standard agent trajectory array. we'll call the array T. It looks like an interleaved sequence. Action 0, observation 0, action 1, observation 1.
Define those terms precisely for a practical setup.
The action is the LLM typing. It's the model generating tokens. It's the internal monologue and the tool commands. So action 0 is the model typing out a Python script.
Okay, and the observation?
The observation is the environment responding. It's the Python compiler running that script and returning a massive text block with a syntax error. That text block is observation 0. Then action 1 is the LLM reading the error and writing a fix.
Now, what is the fundamental mathematical mistake most people make when calculating value over this sequence?
Standard reinforcement learning uses a formula called generalized advantage estimation, or GAE. To calculate the advantage of a token, standard GAE calculates the temporal difference residual, which is the difference in expected value between adjacent tokens.
Right.
It literally links the value prediction of token n to the value prediction of token n plus 1. But here is the critical logical flaw when applying this to agents. The LLM didn't generate the observation. They didn't write the compiler error.
Right. The transition from the final token of action 0 to the first token of observation 0 is discontinuous from the model's perspective. It crosses a boundary from internal policy to external stochastic environment.
Exactly. If you calculate the advantage across that specific boundary, you are forcing your value model, which is only supposed to evaluate the LLM's own choices, to suddenly try and predict the chaotic external output of a compiler.
Which is impossible.
It forces the value model to predict exactly what text the compiler is going to return. That introduces massive, uncontrollable noise into the temporal difference calculation.
So how does SAO explicitly fix the Bellman equation to handle this?
It's brilliant. They introduce the skip observation token level GAE. They explicitly modify the Bellman target calculation in the code. They take the value, the last token of action 0, and they link its temporal difference calculation directly to the first token of action 1.
They literally jump over the environment feedback.
Yes. The mathematical formula connects the reward at the current step to the predicted value of the next action token, explicitly subtracting the value of the current action's final token.
Wow.
It completely filters out the stochasticity of the environment. It acts as if the observation text isn't even there when calculating the advantage gradient.
It is so clean. You only grade the student on what the student wrote, not on the unpredictable exact phrasing of how the grader reacted.
Exactly.
If you are building agentic RL pipelines, you absolutely have to implement this skip observation logic in your GAE function. Never calculate an advantage gradient across an external environment output.
Which leads us to demo 2, the hyperparameter config. For the engineers listening who are spinning up instances right now to try and replicate this, what are the exact specs from the paper?
Let's rapid fire the exact configuration for their agentic reasoning runs. You want to take notes on this. The learning rate for the policy model is heavily constrained. 1 times 10 to the negative 6.
Very small updates. You don't want to shatter the pre-trained weights.
Very small. Batch size is 128. Group size is exactly 1 because, as we discussed, it's a single rollout system. The context budget is massive to accommodate agentic loops. 128K tokens per rollout.
But let's pause and talk about the strict bouncer we discussed earlier, the disk clipping bounds. What are the exact values for the trust region?
This is where the configuration gets fascinating. Epsilon low is set to 0.3. Epsilon high is set to 5.0.
Wait, that is a highly asymmetric window.
It is entirely asymmetric.
Let's break down why. The lower bound is incredibly tight. 1 minus 0.3 is 0.7. So if the ratio drops below 0.7, the token is masked out. But the upper bound is 1 plus 5.0, which is 6.0. It allows a probability ratio of up to 6.0 before the bouncer steps in.
Right.
They are mathematically much more tolerant of the current model being more confident than the ghost model, but they are highly intolerant of it being less confident.
Exactly. If the new model discovers a great path and its probability surges, you want to allow that learning signal to propagate up to a point. But if the new model suddenly thinks a previously generated token is highly unlikely, that indicates severe destructive drift, and you want to shut that gradient down immediately.
That asymmetric logic is a great detail. What about the value model?
For the value model critic, the learning rate is slightly higher, 5 times 10 to the negative 6. And remember the structural hyperparameter, k equals 2. 2 updates to the critic for every 1 update to the policy.
Perfect. Which brings us to demo 3, and I think this is genuinely the most sci-fi forward-looking part of the entire paper. the online learning chameleon test.
This is where we see the true dynamic power of single-rollout asynchronous optimization in action.
Set up the simulation for us. What did they build?
Remember that GRPO and group-wise sampling require a perfectly static environment where you can generate multiple parallel answers to the exact same prompt and cleanly compare them. But in the real world, an agent interacts with the user in real time. The environment is non-stationary. The user's preferences might shift dramatically mid-conversation.
Right. You can't ask a human user to pause while you generate 8 different responses, calculate an average, and figure out what to say next.
Exactly. So the authors built a simulation to test if SAO could survive and adapt in a highly dynamic, non-stationary environment. They created a creative writing task, and they used a separate LLM as a judge to provide the reward signal. But they explicitly programmed the judge to dynamically shift its internal preferences over time without telling the training model.
I love the specific personas they chose for this. It's very internet native.
The judge sequentially adjusts the reward criteria to favor 3 distinct writing styles. First, for the first phase of training, it heavily rewards the cute style. Then, without any warning or resetting of the system, the environment shifts, and the judge starts heavily penalizing cute text and exclusively rewarding the Chunabu style.
For those unfamiliar with the term, Chunabu is a Japanese slang term that basically translates to 8th grader syndrome. It's an exaggerated, edgy, anime protagonist tone. It's a very specific, dramatic, almost delusional style.
It is entirely distinct from cute. And then, again without warning, the environment shifts a 3rd time, and the judge only rewards a highly dry, classical tone.
So the agent is essentially running on a treadmill, and the researchers keep violently changing the angle and the speed without telling it. How does the SAO architecture handle it mathematically?
It adapts like a chameleon. Because SAO uses a state-dependent value model to generate its baseline, instead of relying on historical group average, it tracks the shifts instantly. If you look at the empirical graphs in Figure 5A of the paper, the exact moment the environment shifts from cute to Chunabu, the accuracy for the cute style plummets because the rewards go negative.
Oh, wow.
But the model rapidly suppresses that behavior. Within a few dozen asynchronous training steps, the generation of the Chunabu style skyrockets. It realigns its neural policy to the new target almost immediately.
And what happens when they run the baseline method against it? The standard running mean baseline that most people use.
The running mean baseline calculates its advantage by looking at a historical window of the last 128 rewards. So when the environment suddenly shifts to Chunabu, the baseline's average is still heavily weighed down by the ghosts of the previous cute rewards.
So it's stuck in the past.
It suffers from severe adaptation lag. It takes much, much longer to mathematically realize the rules have changed, and it never actually reaches the same peak performance. SAO is dynamic, responsive, and alive to its environment in a way the baseline just isn't capable of being.
It's incredible to watch the graphs adjust that fast. But as with all cutting-edge engineering, nothing is perfect. The laws of physics and compute always demand a trade-off. We have to pressure test the system. We need to expose the edge cases where this elegant math falls apart. It's time for where it breaks.
Let's start with the infrastructure burden, because the math of SAO relies on something very specific that not all standard data center pipelines support.
Right. We talked about how SAO elegantly drops the need to keep old policy models around by using direct double-sided importance sampling. It just looks at the log probabilities generated during the rollout phase.
Which sounds incredibly simple in theory.
But in practice, across a distributed computing cluster, it is a logistical nightmare.
Oh, absolutely.
It requires your entire network pipeline to reliably preserve token-level behavior log probabilities across asynchronous generation servers, push them through the network, and inject them back into the training servers without dropping a single 32-bit float.
Exactly. When you are generating a 100,000 token rollout, you aren't just sending text back over the wire. You are sending a massive, high-precision array of probability scores for every single token.
That's a lot of data.
If your infrastructure has a network blip, if your backend drops a packet, or if your generation engine doesn't explicitly support exporting those detailed logs natively, which many open-source inference engines don't, SAO completely breaks.
It just fails.
You have no probabilities, your bouncer has no VIP list to check, the importance sampling ratio can't be calculated, and the math fails entirely. Implementing SAO isn't just a simple hyperparameter tweak in a PyTorch script. It requires deep, robust plumbing in your distributed system architecture.
It's a massive data serialization and pipeline challenge. And that leads directly to the Second major point of failure, model scale limitations.
Yes, let's look closely at the limitations section of the paper. SAO was proven on massive iron. The researchers used a Qwen 330B backbone as their baseline, which is a 30 billion parameter model, and they successfully deployed the architecture on the absolute Leviathan GLM 5.2 model, which sits at an astonishing 750 billion parameters.
We are talking about massive enterprise scale.
But the paper explicitly warns that the mathematical dynamics of this system might not transfer directly downward. If you are a scrappy startup trying to fine-tune an 8 billion parameter model, SAO might actually degrade your performance.
Wait, why would a theoretically better, more efficient algorithm hurt a smaller model? Walk me through the logic of that.
Because of the value model critic. Remember, the entire SAO framework relies heavily on the value model being incredibly smart. Smart enough to judge a single complex rollout accurately without a group baseline.
Right, the judge has to be good.
A 750 billion parameter model has the immense semantic depth and representational capacity to act as a phenomenal judge. An 8 billion parameter model's internal representations might simply not be expressive enough to accurately predict values for complex, multi-step reasoning trajectories.
So the small judge just makes bad calls.
Exactly. If the judge is too small, its predictions are inherently noisy. Noisy predictions generate noisy advantages, and the policy model collapses under the weight of bad feedback. Furthermore, if you are working in environments with dense, short rollouts like simple chat alignment or summarization tasks, the asynchronous overhead wasn't your main computational bottleneck anyway. Synchronous GRPO might actually be significantly more stable and efficient for small-scale, short-context tasks.
That is a vital caveat for any engineer listening. You don't put a hyper-advanced Formula One suspension system on a go-kart. The computational overhead and instability risk simply isn't worth the squeeze. Okay. What is the third breaking point? And this connects directly back to your sci-fi chameleon analogy from the simulation. Safety and online adaptation.
This is the philosophical and ethical edge case of the architecture. We saw how rapidly and beautifully SAO adapts to shifting user preferences in the Tunabe test. It is completely fluid. It is highly responsive.
But what happens when you deploy a model that fluid, that rapidly adaptable into the wild, exposed to real, potentially adversarial users on the live internet?
That is the extreme danger. A chameleon adapts so fast it loses its original form entirely. If a model can realign its core neural policy in a few dozen asynchronous steps based purely on environmental feedback, what happens when a coordinated group of users starts feeding it toxic, harmful, or maliciously structured rewards?
The model would adapt to the toxicity. It would optimize for harmful objectives almost instantly, because its entire mathematical foundation is designed to be highly sensitive to single rollout feedback without the sluggish anchoring of a historical baseline.
Precisely. In a real user-facing deployment, this rapid alignment capability is a severe security vulnerability. The researchers explicitly note that deploying an SAO-based system in the wild would require heavy, rigid guardrails. You would need aggressive data filtering on the input side, robust reward monitoring to detect adversarial patterns, and most likely, secondary static safety critics whose sole job is to veto updates before the backpropagation step even happens. Otherwise, the model's greatest mathematical strength, its fluid adaptability, becomes its most easily exploitable attack vector.
It's an incredibly powerful algorithmic tool, but you absolutely cannot just leave it lying around plugged in without supervision. All right, we have covered a massive amount of theoretical and practical ground today, from the hardware bottlenecks to the gradient mathematics. Let's distill this deep dive into actionable, highly memorable points for you, the listener. Let's run through our takeaways.
Takeaway number 1. Synchronous reinforcement learning is a computational traffic jam. If you are running complex agentic tasks with highly variable rollout lengths, from 10-token quick answers to 100,000-token coding loops, group-wise sampling methods like GRPO are wasting massive amounts of your cluster's compute. They are paralyzed, waiting for the stragglers. Asynchrony is the inevitable mathematical future of post-training for complex reasoning models.
Takeaway number 2. Clip hard and forget the past entirely. SAO proves that you mathematically do not need to keep a heavy, memory-hogging archive of old policy models in VRAM to stabilize asynchronous learning. If you use direct double-sided importance sampling or strict VIP bouncer, you can just use the rollout log probs stamped over the network. Be aggressive with your hyperparameter bounds. If the drift is outside your trust bounds, mask the token entirely, zero the gradient, and move on.
Takeaway number 3. A smart critic solves the single rollout variance problem. If you drop the group baseline, you absolutely need a judge. And here is your actionable takeaway, something you can implement in your codebase in the next 24 hours. If you are training an actor-critic architecture right now and your value model's gradients are unstable or exploding, try freezing the full attention layers. Set requires GRPOs. Let the pre-trained attention weights do their job of reading the context, and only update the mixture of expert layers. It kills exploding gradients and drastically stabilizes the whole pipeline.
Takeaway number 4, mind the gap. The skip observation, GAE. When you are training multi-turn autonomous agents, never, ever calculate a token-level temporal difference advantage across an environment output boundary. Jump the math from action to action. Do not force your value model to predict the stochastic chaotic errors of an external compiler.
That brings us to the end of the technical breakdown, but I want to leave you with a final provocative thought. Something that wasn't explicitly tested in the paper, but is heavily, undeniably implied by the online learning chameleon simulation.
Give it to us.
Historically, the industry has thought of model training in distinct frozen phases. You have pre-training, you have supervised fine-tuning, you have RLHF, and then you have deployment. The model is essentially frozen in glass when it finally reaches the user. It doesn't learn from you. But if single-rollout asynchronous optimization allows models to mathematically adapt this fluidly in real-time online simulations without suffering from catastrophic forgetting or gradient collapse, are we crossing the threshold from models that are statically pre-trained to models that are perpetually dynamically alive in their deployment environments? Are we entering the era of the continuously evolving, continuously learning agent?
That is a wild, slightly terrifying, but entirely plausible thought. A model that wakes up a little bit smarter and a little more aligned to your specific workflow every single time it solves a problem for you. So next time you are stuck in a frustrating school group project or sitting in a highway traffic jam behind a golf cart, just remember, single rollout optimization means you don't have to wait for the slowpoke anymore. Just drop the straggler, mathematically calculate your own advantage, and update your own neural weights. This episode is AI generated with Notebook LM based on Single-rollout Asynchronous Optimization for Agentic Reinforcement Learning by Zhenyu Hu, Yuzhang Li, Jitang, Yuxiu Dong. Informational only, not advice.
Like and subscribe if you've been enjoying the journey. See you in the next one.